As we continue our discussion about probability and statistics, we come across another kind of distribution known as a normal distribution. Now, up to this point, we've seen some discrete probability distribution that has a finite number of possibilities. Think of discrete as we don't connect the dots when we graph them. Okay, the in-between values we don't worry about. Think about people. Think about pets. We don't have 1.5. We don't have 1 3/4 pets. We have a discrete probability distribution. We've also talked about continuous probability distribution that can have any value in our interval of real numbers. But what we're going to discuss today is a normal distribution. Normal distribution has data that vary random from the mean, and their shape is a normal curve. Sometimes you've heard this referred to as a bell-shaped curve. Now, this is the important thing to take from this. If you can understand the concepts in this particular graphic, you're going to be able to handle anything we talk about. So we've got our bell-shaped curve here. And we start with that bell-shaped curve. If something is normally distributed, it always has that bell shape. Now, there's a couple ways to look at this graph. I'm going to start with how they built it. They started with the mean right here in the middle, whatever that is, and they go plus 1 standard deviation, minus 1 standard deviation. We've done a little bit of that to this point, but never in the context of a normal distribution. Then they went 2 standard deviations both directions, and they add 3 and subtract 3 to get the layout. And we don't go beyond that, and you're going to see why as we talk a little bit more about that. I did the same thing down here, except I used the notation. Here's the mean, here's plus 1 standard deviation, here's minus 1 standard deviation. Within that normal distribution, the percentages don't change. Okay, I'll say that again. These percentages don't change. So if something is considered to be normally distributed, these percentages are always going to hold. If I go 1 standard deviation both direction, both of these are 34%. 34% of your data fall within 1 standard deviation either direction. So if I add those up, we're talking overall 68% of our data in that first standard distribution. Now, if I would go 2 standard deviations, I have the 34 here. This next part only has 13.5% of the data. And it's the same on both sides. And if I add all 4 sections up, we're now looking at 95% of the data. Now, I'm not going to color this in, but think about if I would color this in, that area is 34%. This area is 13.5. If I add all 4 of those areas, I've got 95% of my data points underneath those 2 standard deviations. Now we can go to a third, but notice the third is getting smaller, and it's only 2.35. It's a very small percentage, both ends. So if I add up all 6 sections here, 1, 2, 3 standard deviations, I'm up to 99.7% of my data. To put this into context, think of an exam. If we would take a test and they would be normally distributed, we would expect 99.7% of the people to score somewhere between 3 standard deviations of the mean. Is there a fourth? Now, we don't go all the way out to a fourth, but there is a small percentage out here and a small percentage left out here. But we're talking 0.3%. It's very, very small. So we catch most of the things between those 3 standard deviations. So it might help to take a look at some examples that are supposed to be normally distributed and ones that we know that are normally distributed. So I've got a few examples here. We're going to start with one that kind of looks like it's normally distributed, but we don't know for sure just by looking at it. We have to dive a little deeper. So we're looking at brown bears, and we're looking at their weights, specifically females. And I notice that the weights are in kilograms. Over here, we're looking at a percentage. Okay, and I should probably put my scale up here so you can kind of follow what I'm doing. So I'm going by fives over there. And the question they're asking me here is approximately what percentage weigh between 100 and 129 kilograms. Before I get to that, I'm going to back up right here. It says these are normally distributed around the mean of 115. So the mean of 115 would sit right in here. So let's put in that bell shape. So it kind of takes that shape on with what it's got here, but they want to know approximately what percent weigh between 100 and 129 kilograms. So I'm looking right here, looking at these three. So this one looks like it's about 25. This one's about 25. It looks like it's a little short. It looks like it's 24, 24. This one looks a little bigger than 40, about 42. So if I go 24% here, and 24% here, and 42%, we'll say there. So we're at 48, 50, we're at about 90%, roughly. It's just an approximation. You might have a little higher, a little lower, but I'm just looking at that. That kind of fits with what we talked about in that normal distribution. We went 2 standard deviations and we got about 95. We're not quite at 2, but we're close. It fits with what we're talking about with that bell curve. We're catching a lot of those data points. The next question they asked was what percentage weigh less than 120? So we're right here. Now instead of adding these up, I'm going to actually add up these two. These are very small. This looks like 5%. This one's really short. That's about 6% altogether. So if I want to go less than that 120, I've got 6% here. I've got another 24% here. So that's 30% on this side. So that side must be about 70%. It isn't exactly normally distributed, but it sure seems to fit those patterns that we've been talking about. So now let's take a look at one that is normally distributed. This is what I want you to be able to do when we talk about normal distributions, is to be able to create one of these. So it says the mean score on a project for some class was 88% with a standard deviation of 5. It says if the scores are normally distributed, sketch out 3 standard deviations. The cool part about a normal distribution, it's always going to take this shape. We know exactly how many sections to put in it. All it's going to change are the numbers. So for this particular example, it says the mean score is 88. So we're going to put 88% right here. Okay, that's the score on their test. They got an 88. The standard deviation was 5. So if I add 5 and I subtract 5, there's 1 standard deviation. If I do it again, and if I do it one more time, there's my normal distribution curve. Now, if I look back at my notes for that normal distribution curve, I know that 34% of the students landed in here, 13.5 landed in here, and 2.35 landed in that last section. Okay? Has nothing to do with the percentage that they scored on the test. The tests are just scores. These are the percentages. So I can answer a lot of questions here. I could say 68% scored between an 83 and a 93. I could say 50% scored above an 88. I could get up here and I could say about 15.8% scored a 93 or higher. I could say the same thing for an 83 or lower. I could say 2.35% scored 98 or higher. And if I put these together, all 6 sections, about 99.7%. Almost everybody scored between a 73 and a 103. Now I'm going to do another example, but I'm going to leave this up here. because the only thing that's going to change with our next example are these numbers on the bottom. So if I take these numbers out, everything else is going to stay the same. So let's read our last example. It says the height of an average American male are approximately normally distributed. They're not perfect, but they almost follow a normal distribution, and has a mean of 69.5 inches tall and a standard deviation of 2.5. I've got everything I need. Notice I didn't change my picture, but now I'm going to change the numbers on the bottom. So if I add 2.5, let's do the high side here. Here I'm going to get a 72. Add 2.5 again. I get a 74.5. Add 2.5 again, and I get a 77. Now, if you're getting confused with this, this is 6 foot tall. This is 6'5". Not a lot of people are above 6'5". Now, if I would go into the NBA, I'd probably have a lot of people that fall up there. But if you think about them compared to the population, they're a very small percentage. Now let's work the other side of this. Let's work backwards. So if I subtract 2.5, I'm sitting at 67 inches. And if I subtract 2.5 again, and if I subtract it one more time, now 62 inches is 5'2". And if we're talking about average American males, we don't have a lot of average American males who are shorter than 5'2". Okay, once they're done growing, they're usually somewhere. 99.7% of the population for average American males is somewhere between 5'2" and 6'5". So this is a normal distribution, an approximate normal distribution. And I can answer a myriad of questions with this. The first question I ask is what percent are between 67 and 74.5? So I'm looking right here. So I take 34 plus 34 plus another 13.5. So I've got 68 and 13.5. I have 81.5%. So I can answer this one with 81.5% are between those two heights. The next question I ask are what percent are taller than 6 feet? Now they're trying to throw you off here, but 6 feet, I know that's 72 inches, so they're looking right here, and I'm looking that direction. So 13.5 and 2.35, we're not going to worry about that small percentage that's above there. That's a bit of an outlier, but we're getting close here. About 15.85, roughly 16%. So I can say about 15.85% are taller than 6 feet. Where we have to be careful is when they jump out of percentages and they start talking about numbers. Now, it's real subtle, but this last question says, if I have a group of 2,000 men, how many are taller than 6 foot? It looks just like the question before it, but they gave me an actual number. So if I take that 15.85%, and I'm going to turn that back into a decimal, 15.85%, and I multiply it by 2,000, now I have an actual number. Okay, I would have an actual number of how many men I would expect to be taller than 6 foot if I would look at an average group out of 2,000. Okay, so be careful when they start asking for how many as opposed to what percent. How many, we still have to find that percent, but then we have to multiply by how many people are there. All of these are normal distributions, or at least approximately normally distributed, so these percentages are going to hold. They're going to work for a lot of the problems that you tackle with normal distributions.